Chapter 3 is about variables and histograms. First, we're going to talk about variables. A variable can be any characteristic of a person or thing that we want to study. So for example, in a health study, we might be interested in people's blood pressure, weight, height, cholesterol level, etc. So more variables that we could talk about could be age, height, weight, income, family size, race, religion, etc. And if we're going to talk about variables, we're going to want to talk about types of variables. So first we have what's called a quantitative variable. Quantitative variables are described with numbers. Quantitative variables could be age, height, weight, income, family size, anything you could describe with numbers. A qualitative variable is measured by a category, or you could only describe it with words. So things like occupation, race, religion, eye color. And then we can break it down even further. So you can be even more specific. So quantitative variables can be discrete or continuous. Discrete variables can only vary by a fixed amount. So you can have the numbers like 0, 1, 2, 3, 4, etc. Whereas continuous random variables can be any number in an interval, and so that means lots of times we'll have nice decimal numbers. Those would be continuous numbers. So again, discrete, they can only vary by a fixed amount. So something like family size, because you can either have one person or two or three or four or five. The number of classes you're taking, because you can take one class or two classes or three classes. And then also you could vary by a fixed amount where it's like half a point. So when I grade quiz scores in half-point increments, your scores could be 0.51, 1.52, etc. Now, continuous means variables, the values can vary by arbitrarily small amounts, or you can be any number in an interval. So for your age, we usually say that we're just 20 years old, but really it could be 20 years and 3 months and 2 days and 5 minutes and 3 seconds, and really you can just keep going and going. So age, height, weight, income, etc. Now your continuous variables are always recorded to a certain number of decimal places because we don't like to just write decimals that go on forever. So they may look discrete. So again, your age in years, you might report that you're 20 or 21 or 22, but really you're 20 years, 3 months, 5 days, 2 minutes, etc. So our flow chart, so you can keep track of it, is variables can be either qualitative or quantitative. Qualitative just means words or categories. Quantitative means numbers. And then the numerical variables, quantitative, can be discrete or continuous. A histogram is a graphical tool that we can use to summarize quantitative data. So for example, I randomly selected 32 salaries from all USU employees. Now these numbers do include benefits. The employees don't actually see this much money. So here is our data. Okay. Notice that it's very difficult to make sense of a list of numbers like this. Okay, so one thing we could do is put all the numbers in order. And that does make it a little bit easier to see. At least I can see the smallest salary is 148 and the highest was 219. But it's still very hard to envision that data in a list. So we can try and summarize it. So what I've done is I've broken up the salary range into intervals. So 0, $20,000, $20,000 and $40,000, $40,000, $60,000, etc. Up to $120,000 to $220,000. And then I figured out the number of employees that fall into each category. And then I changed those numbers into percentages. So this would be 18.75%, 18.75%, etc. Now we want to find a way to make this a graph. So we could try to graph the percentages as the heights of our bars. But unfortunately, this is the wrong method. It's really easy, but it's the wrong method. So let's see why. So if I was to graph this, I say, okay, so from 0 to 20,000, there's 18.75%. So 0 to 20, about 18.75. From 20 to 40, we need another 18.75. 40 to 60, another 18.75. Then 60 to 80, we need 21.8. And then for 80 to 100, we need 9.3. And then a 3%. And then from 120 to 220, we need 9.3. So what is wrong with just graphing percentages? What is wrong with this graph? Why does this look so strange to us? It's all in that last interval. When you look at this graph, it seems like a lot of people are earning a lot of money. The reason why is that the area of that last block is so big compared to all the other areas. And our minds, when we look at it, we just look at the areas as the overall percentage. And so the area of this block is so big because the length of it was so big. Because all of our other increments went by 20 except the last one. So all the increments went by 20 except for the last one. And so again, that makes the last block very big. It's disproportionate to all the rest of the blocks. So what can we do to fix our histogram? There are two different things that we could do. Okay, the first is that we could make all the widths the same. And this is what most people do. And it's actually the easier way to do it. Unfortunately, it's not the way that we do it in our textbook. In our textbook, what we're going to do is we're going to change the scale. So we make the areas represent, the percentages instead of the heights representing the percentages. That way everything will be proportional and it will look a lot better to us. So this is how we're going to do it. In a histogram, the blocks represent the percentages. So the area of the block is proportional to the amount of the data in the corresponding interval. The areas of the blocks represent the percentages. So that's the part you need to remember. That the areas represent the percentages. Now the total area represented by the histogram is 100%. So let's go through our steps for drawing the histogram. First, we have to determine the percentage in each interval. Then we calculate the width of each interval, and then we need to find the height of each interval. Now when you think about it, for a rectangle we know that area equals width times height. If I was to rearrange that equation, then height could be equal to the area divided by width. Technically, I'm just dividing both sides of the equation by width. Now, if I was to change this into our statistical terms, the area represents the percentage. So it's just the percentage divided by the width. So we find the height for each one. We're going to draw the blocks for our appropriate class intervals and then label the axes. And we'll come back and talk about how to do that. So coming down to our table again, so we have our intervals. I've counted up the number of employees that fall in each interval for you. And then we have the percentage of employees for each interval. So now let's go through and figure out the interval width for each one. So if you go from 0 to 20, that has a width of 20. 20 to 40 also has a width of 20. 40 to 60 has a width of 20. They're each 20, except for the last interval has a width of 100. Then for the interval height, again, we said all we have to do is percentage divided by width. So this will be 12% divided by 20, which gives us 0.6. And then my next percentage is 12 divided by 20 gives me 0.6. Sorry, I just remembered that when I wrote this table before, I divided by the wrong number of employees. I did 50 employees instead of 32. And I fixed the percentages up above, but I didn't fix them on this page. So let's just go ahead and quickly copy down our correct percentages again. Okay, now let's go through now that we have our correct percentages and calculate each interval height, which again is our percentage divided by the width. So my first percentage is 18.75 divided by a width of 20, which gives me 0.9375. So that will be the first three will each be 0.9375. Then my next one I'll have 21.875 divided by 20. 1.09375. And then if we have 9.375 divided by 20, that's 0.46875. And 3.125 divided by 20 is 0.15625. And 9.375 divided by 100 is 0.09375. Now that we've calculated each of the heights, we can go through, and I need to draw my scale over here. Let's maybe go by 0.2. 1.0, 1.2. Okay, now for each interval, we're going to graph our new height. So for 0 to 20, we're going to go up to 0.93. 20 to 40, and 46 are all at the 0.9375. And then 60 to 80, we're going to be at 1.09. And then 0.468. 0.156 and 0.09375 for our last interval. Notice that our graph looks so much better now. Now I look at that and it seems like not as many people are making a ton of money, which represents our data much better. So this is a much better graph. And then if you remember, I said we're going to come back and talk about how to label our axes. So let's go back up and read about what it says. So label our axes. The units of the horizontal axis correspond to the variable being graphed. So we are talking about our salary in thousands of dollars. So the x-axis would be salary in thousands of dollars. Then for the height, remember how did we get the height? We took a percentage and we divided by the width of our interval, and our interval is in salary, thousands of dollars. And so this is technically our percentage divided by thousands of dollars, like 100,000s of dollars. And so over here, this would be our percentage per $1,000. It sounds like a very awkward label, I know, but that's what it's always going to be. So the units of your vertical, your y-axis, are percentage per horizontal unit. So if x is high in inches, then the y label would be percent per inch. Or if x is weight in kilograms, then the y label is percent per kilogram, etc. The next thing we want to be able to do is calculate percentages from a histogram. And it's really not too bad to find the percentages from the histogram, as long as you just remember that the percentage represents the area. And area is just width times height. Now to do this, we do have to make one assumption, which usually isn't true, but we assume that the data is equally spread throughout each interval. Okay, so example 18, the exam scores and points for 250 students are summarized in the table below. So for each interval for the score, like 0 to 50, 50 to 70, 70 to 80, etc. And then I've counted up how many students are in each interval, the percentage of students that is, the interval width, and then for the interval height, remember that the height is just the percentage divided by the width. So let's first draw a histogram, and we don't want to forget to label our axes. So my x-axis would be my units that I'm measuring in, my points for the exam score. And I'm going to use a scale of 20, so 0, 20, 40, 60, 80, 100. Oh, I don't need to make it that small. Let's make it a little bit bigger. So 0, 20, 40, 60, 80, and 100. And for my vertical axis, I will do every 3 blocks as 1. For my y, label, remember it's your percentage per horizontal unit. So if we're talking about points, it's going to be percentage per exam point. So my first interval from 0 to 50 has an interval height of 0.2. And then from 50 to 70 we can go up to 1. And 70 to 80 we can go up to 3. 80 to 90 we can again go to 3. And 90 to 100 we can only go to 1. Sometimes if you want to shade in the blocks, it makes them a little bit easier to see. So there's my histogram. It looks like we have a lot of people in the 70 to 80 range. Notice that I had a lot of different interval widths, so it's a good thing that I changed my to heights instead of just graphing the percentages. So now I can ask you questions like, do you think there are more people with a score close to 60 or a score close to 85? And now all we have to do is look at this graph. So a score close to 60, that would be somewhere about here. A score close to 85 would be somewhere about here. So which one do you think that there are more people? I would say there are more people that are closer to 85. Then I might ask you something like, are there more students with C's or with A's? Now C's, by definition, the common definition is that means that that's 70% to 80%. And A's are 90% to 100%. So to do this, I could go up and say, okay, C's, that's from 70 to 80, so that would be this block right here. So 70 to 80, that would be this block. 90 to 100 would be this block. Obviously, there's more area in this block from 70 to 80. So there's more with C's. Then I might ask you something like, what percentage of students scored 80 or above? Now we're just looking at a graph, so this isn't going to be incredibly exact. But what percentage of students scored 80 or above? So what I'm going to do is reproduce that part of my graph, so 80 and above. So we have that 80 piece. So from 80 to 90. And then 90 to 100. And the 80 to 90 piece had a height of 3, and the 90 to 100 piece had a height of 1. Now remember, the percentage is just related to the area. And area equals width times height. So if I can just figure out the area of each one of those rectangles, I can add them up. So my first rectangle has a width of 10. 80 to 90 has a width of 10. And then the height was 3. And then my next rectangle has a has a width of 10 as well, but a height of only 1. And so my two areas are 30 and 10, which add up to 40. So 40% of our students scored an 80 or above. The next question says what percentage of students scored less than 70? So we're going to do the exact same thing. We're just going to sketch it out again. So we can go from 0 to 50, had a height of about 0.2, and from 50 to 70, we had a height of 1. So my area is going to be, okay, we had a length of 50 times a height of 0.2 plus a width of 20 times a height of 1. And so that adds up to 30%. If we turn the page, I've reproduced the histogram for us so that we can continue working on this problem. This is just our same problem. So number 6, what percentage scored at least 60 but less than 70? So this one's interesting because 60 wasn't actually one of our dividing points. Okay, so we're looking for this rectangle right here, and that's why we assume that all of our points are equally spread between the 50 to 60 and the 60 to 70. And so we would just draw it out. So from 60 to 70, we had a height of 1. So my area, which equals length times height. So I guess we've been saying width, not length. So my area has a width of 10 and a height of 1. So that gives me 10. So 10%. And what percentage scored at least 25 but less than 55? So from 25 to 55, to 50, our height was 0.2. And from 50 to 55, our height was 1. So first we have a width of 25 and a height of 0.2, and then we add on our width of 5 times our height of 1, and so this gives me, again, 10%. So you can get very creative in these questions. Again, all we're really doing is finding areas. Width times height gives us areas. Then I might make it even harder, and I might ask what interval contains the 50th percentile. Now 50th percentile just means that 50% of the data is less than the 50th percentile. So we're looking for the median or the middle point. So what I'm going to do is I'm going to go through and add up all of my percentages and see about where 50% would lie. So I'm going to start at the bottom. So start with my lowest number. So my lowest number is from 0 to 50 with a height of 0.2. So if I multiply that out, so 50 times 0.2, that gives me 10%. So I'll just make a note of that. So I have 10% in the first block. So I'm not up to 50%. Now let's look at our next block. So our next block goes from 50 to 70. It has a height of 1. So 20 times 1 gives me 20%. So we're at 20% in this block. Okay, and so far, 10% plus 20%, that only gets me up to 30%. So let's go one more. From 70 to 80, it has a height of 3. So 70 to 80, that has a width of 10, and a height of 3, that would be 30%. So 30%. Well, now if I add all those together, so 10% plus 20% plus 30%, that would give me 60%. So that's over 50%. So maybe I went too far. If we added just the first two together, 10% and 20%, that's only 30%. So I know I need more than the first two rectangles, but if I add on the third rectangle, I've gotten too much because I'm trying to figure out where the 50% would be. So my 50% should be somewhere in between that 70 and 80. So my final answer is that it's between 70 and 80 points. And number 9, what interval contains the 75th percentile? Or in other words, 75% of the data is less than the 75th percentile. Or we could ask, which interval contains the exam score that's greater than 75% of all the other exam scores? So we're going to do the exact same thing. We'll go ahead and use the data that we already know. So from 0 to 50, that's at 10%. And 50 to 70 is at 20%. And 70 to 80 is at 30%. And we know that only adds up to 60. So that's still too low because we're trying to find 75%. So now let's do my next interval. So from 80 to 90, that has a height of 3. So let's see, 3 times 10, or 10 times 3 to keep with our same format we've been writing it in, gives me 30, so this is a 30%. So let's add that one on. So 10% plus 20% plus 30% plus 30% gives me 90%. So 60% is too low, 90% is too high, so that means I would have hit my 75th% somewhere in that interval. So it's between 80 and 90 points. Now, almost more as a side note, we could talk about histograms for discrete variables. Histograms for discrete variables are sometimes done differently, so usually each class interval just represents a single number and the number is placed in the middle of the bar. So this is a histogram showing the distribution of families by size. So not a big deal, this isn't something you really would have to worry about, but just so you've seen it. Notice our histograms again look slightly different. We just graph the bar from 1.5 to 2.5. Even though you don't have a family with 1.5 people, this is how we graph it. Now there's a term called distribution. So the shape of the histogram is often referred to as the distribution of the data. And smooth histograms are often used as well as block histograms. So a smooth histogram just means something where I draw on the curve like this. So I try and follow the data with the curve. And the interpretation of these histograms is the same, that the percentage is represented by the area under the curve. So this is a smooth histogram showing the distribution of families by income. And just kind of for fun, try and bred rats to see if you could create brighter rats with selective breeding. After 7 generations of breeding, he had 2 strains of rats. He measured their intelligence by the number of errors they made in a maze. So which distribution do you think represents the maze bright rats and which represents the maze dull rats? So remember, the number of errors, the brighter rats make less errors. So this graph seems to have less errors. So this would be the maze bright. Whereas this graph, which they differentiated with the dashed lines, it has more errors overall, not all of them, but overall have more errors. So these would be the maze dull. So those are just a few examples. And just real quick, just so this is something you've seen, we're going to talk about the different types of histograms. So different disciplines use different versions of histograms. We learned how to do what's called a density histogram, where we represent it by percentages. But many people prefer to graph just the frequencies or percentages instead of having to do the percentage divided by width. because it's a lot easier. But keep in mind, this only works if the class intervals are all the same width. Sometimes you can do this, sometimes you don't have all the data for all the intervals, and so you can't do it this way. And so I went through and I actually looked at our same data because I had the raw data, and I did the salary intervals with an interval width of 20 for all the intervals, number of people, and the percentage of people. And then I graphed the histogram with just the frequency. So I just graphed the number of people in each category. And so that's what the histogram of our original data looks like if you do equal widths. It does look a little bit different than the histogram we came up with. And here's the same histogram, but I graphed the percentage instead of the count of people. Notice the shape is exactly the same, we just have a different scale on our axes.